Okay, the topic of torque is next up. Now we're taking just basically a rudimentary approach to it. This is a very complex subject, but we're going to take a situation where we have a bar with a center of mass and we're hanging things from it. It's going to cause it to rotate one way or the other. Definition of a torque is a perpendicular force applied to a system causing an angular motion. So if I were to take a meter stick with a fulcrum on it and I put it right here, it's going to rotate counterclockwise this direction. If I put it on this side, it's going to rotate clockwise in this direction here. So I hang a bunch of weights on there. I want to see what the overall torque is going to be and how to counterbalance it, form an equilibrium. So rotational motion is being created here, and if we take if you have watched that video of the REO Speedwagon, if the crank that guy used was a 15 centimeter crank, and it took 225 newtons to crank the thing, then the amount of torque that he has created, once we change the centimeters over to meters, is 33.8 newton meters, and newton meters is the label for torque. So in the example I gave you there, we have this scenario right here in black for the first three parts of it. The fourth part is where the red comes in. We'll come back to that. I have a 40 kilogram iron rod balanced on the center mass directly, but it's called a regular rod, which means that the center mass is directly in the middle. And I'm hanging, I'm placing a 10 kilogram mass, or weight, I could be hanging it, doesn't make any difference. Probably make more sense to be hanging it. And then a 5 kilogram mass over here. And I want to know what is the overall torque if the center mass is where the fulcrum is placed. And the fulcrum is the point at which it's tipping, one way or the other, like a seesaw tip. So the first question we ask is, what is the overall torque of this scenario? So we take a look at the left side of the fulcrum and the right side of the fulcrum. This torque is defined as the R, which is the distance or the radius, however you want to talk, when it becomes a circle as it rotates, same thing. And the perpendicular force is being pulled towards the center of the earth, the gravitational pull here. So it's a 10 kilogram mass, 98 newtons. It's on the 1 meter mark where the fulcrum is 3 meters, so that's a 2 meter distance. Multiply those together and we get 196 newtons per newton meter, no per, it's multiplication. And it makes sense because you've got this bar, you hang the weight on the left side, it's going to rotate and form, if it were to continue circling around somehow, it'd be fun to watch, that would be a counterclockwise direction. So that's a counterclockwise torque. On the right side, we have hanging a weight of 5 kilograms at the 4.5 meter mark. The weight is 49 newtons, that's your perpendicular force. Multiply that by the distance from the fulcrum, which is 1.5 meters, and we get 73.5 newton meters clockwise. So our overall torque, our net torque, is the difference between the two. There are opposing forces there, and since the counterclockwise is larger, the difference is going to be 123 newton meters counterclockwise, is how that would spin, if it were to spin. The second question I asked on there deals with what is the force needed to be applied at the zero mark to establish equilibrium. In other words, what am I going to have to do to the left side to make sure it doesn't do the spinning thing? Well, I know the torque, overall torque, is 123 newton meters counterclockwise, so that means I'm going to have to apply something 123 newton meters clockwise to establish equilibrium. So in other words, if I have like a weight hanging on a rope and I attach the rope to the end, the 0 point, or very close to it, or tape it on there so it's right on the 0 point, then I use that equation, tau is equal to 123 newtons times the distance times the perpendicular force, and the perpendicular force then is going to be 41.0 newtons upward. So I'm going to apply a force of 41 newtons to keep it from spinning. It's perfectly placed. This next problem is if I put this on the right-hand side, what does the force need to be applied at the 5 meter mark in order to establish equilibrium in what direction? So at the 4 meter mark, we know that tau is 123 newtons. That's the That's the counterclockwise torque taking place here. I'm going to have that multiplied by Ft. Now, think about this. If you have that weight, I'll go back over here. If I have this system right here, and at the 5 meter mark, I'm going to place something here. If I either lift it up or pull it down, well, since this is already going this direction, I don't want it to continue going in this direction. So I'm going to have to attach something right here at the 5 meter mark. So it's got to go downward to counterbalance the downward force over this side. They got to equal each other and form equilibrium. Okay? So, since, or the 4 meter mark, not the 5 meter mark, 4 meter mark. So 123 newtons equals 4 minus 3 meters times F perpendicular. So that force must be a downward force of 123 newtons in order to establish equilibrium. Now the next scenario is an interesting one because now I'm moving the fulcrum off of the center of mass. And so I go back over to the drawing I have here. So I moved this, slid this over to 4 meters. So now the center of mass now comes into play in this. The center of mass now is going to be part of the force pulling this in a counterclockwise direction. And this poor little 5 kilogram mass is on its own trying to counterbalance it, which it can't do. So the question is, what is the overall net torque in this situation? We have to now include the fact that we have a 40 kilogram mass here, which has a force of 392 newtons. The weight is force, and that's 392 newtons. And it's in conjunction with this 980 newton, or 98 rather, newton force weight attached here. We're over here, we have half of that with 1 meter, so it's like 24 and a half over there. So that means it's going to be heavily counterclockwise. So let's take a look at that. Left side of the fulcrum, we've got the 294 newton meter of that 1 meter that we did before. And the fact that we have, that is not correct. That's supposed to be, fix that right there. That is supposed to be 392 newtons right here, not 9.80, so make sure that's correct on your notes. The right side, so we still have that 24.5 newton meter torque over there. So the counterclockwise torque is 24.5 newton meters. The counterclockwise, the clockwise torque is 24.5 newton meters. The counterclockwise torque is 686 newtons, wildly favoring the counterclockwise by a difference of 662 newton meters. So that will be your overall torque for that scenario. Okay? You've got some practice problems based upon that. Have fun!